All right, thank you everyone for sticking around. Those were great talks earlier on, but I would like to get started with our next talk and introduce our next speakers. I'd like to introduce Peter and John, and they'll be doing our next talk. Thank you.
Hi everybody, thanks for having us. My name is Peter Smith. I'm the founder and CEO of Edgewise Networks. I'm joined here by actually our first employee and chief data scientist, John O'Neill. John is the brains behind the operation. He's actually Dr. John O'Neill, PhD from Harvard in a variety of things. He'll be giving his talk in French or Italian. His PhD is in linguistics. Oh, Sanskrit, perfect. So no, we'll try to keep it to English. And the point of the talk is really about how do we establish multiple different perspectives on our network attack surface. So I was at Black Hat this past season, and I was standing in line at a Starbucks for coffee. I see this kid walk up to an ice cooler. He grabs a bottle of milk and drops it in his pocket. And I'm like, wow, that is brazen at a casino to steal something. And so I immediately look around to see where the cameras are, and I notice a bunch of them. And the thing was that the environment had changed. There were other people surrounding this kid, so from every perspective that the camera was in, they couldn't see this kid put something in his pocket. And it got me thinking, you know, perspective is really the most important aspect of observing your network. And the majority of what we do today is a fixed perspective. And it's, in most cases, actually just a single point of view of the network. And how can we broaden that to do some interesting things? I won't kill the punchline. I'll save the interesting things for later on in the talk. But quick agenda here. I'll give you a little background on the problem. We'll talk about what we're doing today as a solution, why we think there's a better approach. Everything that we show you is free open source. It's something that John's been working on as somewhat of a side project at Edgewise, and it's on a GitHub repository, which we'll share at the end. And then we'll cover why it's a better solution. And then I'll hand it over to John, and John's going to get into the details of what this thing actually is, how it works, right down to the graph analysis that we're using to make all of it function. So there could have been a different title for the presentation. It could have been, it's all a matter of perspective, right? Instead of multidimensional attack path analysis, which sounds very, very fancy. So what I mean by a difference in perspective, I have one perspective of you guys right now, right? I'm looking at all of you. I can see all of you individually. That's a single perspective. Me looking out into you, the network. We do this every day. That's a Nmap scanner sitting on some box scanning your network, right? Multi-perspective would be distributed Nmap. You're all running Nmap, looking at me, looking at your neighbors, I'm looking at you, we aggregate the data, and now we've got a multi-dimensional perspective of the attack surface of the network. Now, the next part is position. Right now, because of this microphone, I have a fixed position. I can only see the fronts of you. But there's no reason that I couldn't walk around and see the backs of you. And so the position is also important. Can I change my orientation relative to the attack surface? Do I have a single view of the attack surface or multiple views of the attack surface? And there's really interesting things you can do once you have all of this data in one place and you can do some analytics on it. But before that, I think there are some interesting physical analogs to this that are worth pointing out just to make the points crystal clear here. So this is a friendly neighborhood coffee shop. And what it's showing you is the perspective in the coffee shop of their camera. It is a single perspective looking over the counter into the customer environment, and it's a fixed position. I think it's actually kind of interesting as a side note that a lot of these camera angles that you're about to see, they are indicative of sort of our social values. When you look at this, and what it's saying is that there is no camera down into the register's cash drawer. So they trust the customers, or at least they feel like their processes would figure out if somebody was stealing cash out of it. They aren't monitoring the clerks. They are just looking at the customers. Now, if we change our view, this is any cybersecurity conference, Black Hat, or a casino. What we see here is 22 cameras, just in this one view here. It's multi-perspective, but they are also fixed position, right? They've got a lot of different dimensions of visualization of the total attack surface. Now, we could do something else, which is actuated cameras. Change your orientation, or a robotic camera. Actually, I used to work out of Manhattan for a company in Boston, and I had one of these robots in the office. And even though I had a fixed position or perspective, I could actually move myself around so I could get different orientations and views of my surroundings. You can take this to an extreme, and what we have is drone swarms, right? So each independently movable, and each with its own perspective. I mean, the military does this on a daily basis, right? You're surrounding an object to get every vantage point you can, each individually movable. So I thought it would be interesting to do a case study. So I walked into a convenience store with a camera to see what their perspective was in terms of the floor layout, what the obstacles were from your ability to look into aisles, so on and so forth, and how they position cameras. So what you can see here is through the front door, there's 2 cameras. When you're looking down an aisle, it's worth noting there are 4 aisles. Only 2 of them have camera coverage. And then the cash register, again, this is a social values problem. The cash register has 3 cameras. A cash drawer camera, they clearly are looking for the insider threat, stealing money out of the cash drawer. There's the perspective of the customer at the counter, and then there's the perspective of the clerk at the counter. So I think what this tells us is they don't care about people stealing candy bars in aisles because they can't even see down 50% of their aisles. They clearly care about the cash in the cash drawer. So what I did, is anybody here willing to admit that they watch the Property Brothers on HGTV? Okay, perfect. So this is the Property Brothers view where we're gonna do the home makeover here. We're gonna drop in the counter with the cash register, put in a couple aisles. We're gonna put the cooler around the sides and then the door out the back. And we'll drop in the cameras just as I saw them in the photos. So there was the camera that was on the front door. There were actually 3 cameras on the cash register. There were 2 cameras on 4 aisles. And there was a camera in an open general space. And what we can see here is that there's actually quite a bit of gaps in their view. 2 of the aisles aren't covered. There's the back corridor that's not covered, and this general open space that's not covered. So really what my point is here is that when we limit our perspective of the attack surface by having fixed vantage points or single views, what we're doing is leaving blind spots, whether that's your network or the local convenience store. So I'm sure you're all wondering, why am I talking about convenience stores and stuff? Yeah. It is highly relevant to cybersecurity. And it's because of this. How do we scan our networks? Do we use single perspective or do we use multi-perspective? If you've got a Rapid7 scanner that is sitting on some box in some secure enclave that has all of your security tools, you are using a single perspective, and it is a fixed position. It's not changing. So what are other examples where it would be multi-perspective? If you have a SIM, that's multi-perspective, right? You're aggregating logs and correlating the events from multiple distinct perspectives. If you're using Insight IDR from Rapid7 as an example, and I obviously don't work for them, but I'm a big fan of that product, you would be collecting this sort of information from desktops, which are movable devices. So that's an example of multiple perspectives on movable devices aggregated into a single location and having correlation done across it. So what is the real main point of this talk? It's this. It's that one of the most important things we do from a single perspective, and we should start doing it from a multi-perspective to get the multi-dimensional data, and that is network scanning. So right now, you're gonna scan your network with a single Nmap, and you're gonna tell your administrators to open up the firewalls to allow access so that your Nmap can see everything. Well, that's great that it can see everything, but what it can't see is what the pathways are between the hosts that you just scanned. Those are the pathways that the attacker can use to move laterally. and you don't actually know what the perspective is from the domain controller, what the perspective is from the file server. You know the perspective from the perspective of the Nmap system. So what if I told you that we could make every system in Nmap, and every system scanned every other system, so you had this multi-dimensional view of the total attack surface of the network? Instead of me telling you that the network looks like this from the scanner's perspective, I can actually tell you what the network looks like from every perspective, and that's super powerful. And when I say we're going to make every device a Nmap scanner, in the bottom right-hand corner there, I'm actually saying that you would deploy Nmap or distributed Nmap to every one of your servers, every one of your cloud instances. I mean, if you're up for it, you could do it to desktops as well. And once you aggregate this data, then there's one more step to make it really compelling. What if we could overlay the vulnerability information for all of the scanned ports onto the edges of these connected vertices? Every host is a vertex, right? And they're connected by edges, which are the paths that you've learned from the Nmap scanning. And if I can overlay vulnerability data, then you know what I can do? I can do a graph analysis to identify the open, shortest, vulnerable path between any 2 points. So the one on the left might be the internet, the one on the right might be a core database with all of your credit card information. And if I know the connectivity and the potential connectivity, this is not used paths. Scanning is telling me what is possible, not what is used. That's the purpose of Nmap, right? So if I can say that there is potential connectivity between all of these and the services that are listening are vulnerable, then it's one graph analysis away from telling you a path from a vulnerable entry point to the vulnerable target through the mesh of services. And that's exactly what we're going to do, and John's going to show you how that works. Before we get there, why do you care about this? Well, you care about it because there are 19 vulnerabilities published every day. 4 of them are critical: remote exploit, root compromise. It takes an average of 50 days if you've got everything in order to remediate on average across the industry. And what that means is that there's perpetual exposure, and you are likely needing to prioritize. What better way to prioritize than to identify core assets, the paths to them that are vulnerable, and start picking off the closest vulnerable paths first, and then focus on the rest. So prioritization is number one. Number two, it's to fortify the paths from internet-connected systems. So you know your core assets, and you can easily identify with this approach every entry point that receives globally routable address space. So now that you know all of your globally routable entry points and you know your asset, you can map every path between them. And the point is, do you have appropriate controls in place at all of those intermediate junctures in the network? If not, you've got a task to do. That is a very clear gap that needs to be closed. Number 3 is network overexposure. So it's probably not a familiar term. It's something that we made up at Edgewise, but network overexposure is how many paths to a given target did I discover versus how many of those are actually needed. So I've got a database that has the potential to accept 100 connections from various sources, yet only 10 of them are actually needed. I'm 10 times more exposed on that database than is necessary. So how do you accomplish least privileged access on the network to ensure that only the required entities are communicating and only the required entities can communicate? So this is sort of laying the groundwork for a segmentation project or micro-segmentation or something that would constrain access to those core resources. I think at the end we should have a chat about how would you use this data. This is just 3 possible options. There's a multitude of ways you could leverage this data. Before I hand it off to John, the only thing that you didn't come here to learn how to use Nmap. I'm sure everybody in this room knows how to use Nmap. I just brought this slide up to point out that there are really 2 ways to get this highly dimensional data. Number 1, you can use dnmap, distributed Nmap, which is really just a wrapper that orchestrates some of the heavy lifting around collecting these Nmap files from a variety of sources. But probably the easiest way is just to use a configuration management system. Puppet, Chef, Ansible, SaltStack, SECM, whatever you happen to use. And you can just have it execute the Nmap. You're going to give it a very broad set of ranges that it should scan, and then collect the resulting file. And once you have that, that's when what John is about to tell you is really important. So everything he's about to tell you is available here. I have the domain attackpath.com. I hadn't had enough time to redirect it to this, but over the coming days, I will redirect attackpath.com to that URL. And with that, here's John.
Worked, good. In fact, when originally in the slide he had attackpath.com, and I thought, oh, he's making a joke. He's waiting for me to put in the right URL. Anyway, so this is not so much a slide as it is a Jupyter notebook. So hope you don't mind that too much. Also, I've been writing this code in real time, so if you like going to the circuits to see people falling off the high wire, this is where to be. So what I did, of course, was write this in Python. I had actually, I was out of the office until Thursday morning, and then I was told, oh, by the way, how would you like to do a talk on Saturday? Sure, no problem. Can you do this? And can you here's the description. Can you program this? I said, well, I've got some of it already done, so I guess so, yeah. So let's see what happens. So I'm just importing stuff here. Now, what we're actually doing here is starting with the Nmap data, which Peter just talked about, which implicitly has inside of it all the network topology we need to know. We want to import that. And I won't go into that deeply because it's really boring to parse files and not too hard. But taking that and then turning it into a graph structure. Using that graph, and then we'll use that graph, use a few examples of using that graph just to find the shortest paths from internet accessible hosts to some target. And after we do that, we'll then apply the vulnerability data. We'll talk about the vulnerability data. We'll then apply it to the graph and then rerun that same, going from shortest path to most vulnerable path. And then there'll be some graphics so you can actually see instead of having to read a lot of, print statements. Implicitly, by the way, just, it's at some level of abstraction, of which the Nmap data is just source IP, destination port, and service. So, and the typical Nmap data looks like that. Now, let's start with, go down, and then we'll start with just the first thing. We'll get a nice small graph. We'll start with a nice small graph, and it'll define the initial target. Now we have the graph. G is just the graph, and we'll start. What we want to do is actually find paths in that graph, going from a selection of internet accessible nodes to the target, which we've named. Now, what I'll be showing you is there's a couple ways we can do this. We can talk about, if you want the n most vulnerable paths, we can return that. But you can also, we'll be doing all the paths with a weight less than a distance less than a certain score. And there are several search techniques available. I'll go back to this in a second after I show you. So let's actually, we can get the paths. I'll come back and do this. And then just go down to the first picture so you can see what I'm aiming at here. Oh. Actually make that, you see the whole thing. Well, let me make this a little less big. No, it's really not going to help me on this. See if this will work. Okay, maybe there. Oh, we can see that. All right. Basically, this is just the first graph we'll see. the red node is the target, the green nodes are internet accessible, and you can see the red paths there. And we'll come back to this graph later. But if you look at the, say the first path, we see it's 2 hops from 22 to 16 to 228. And in this case, it's 22 is here, 16 here, 228. Pretty straightforward. Now, it's a little bigger again so we can read it. Less bigger than that. There are lots of ways to find paths in graphs. A lot of them are specialized in finding the single extremal path of some sort. And since we're not interested in finding only one, what I did was implement a sort of a quick version of beam search, which essentially incrementally advances through the graph from the target outwards and looks for the least expensive way to get to each node, or keeps a small number of them, and then keeps spreading out until it finds the internet accessible nodes, and then returns the scores that it finds for those internet accessible nodes, which is basically what I did to get these scores. Now, given it a weight of a distance of 3, we only had 3 paths here, so we could actually reduce it if you wanted to know less. Just redo that and get 2, and then redo the chart, and we see, again, not very exciting at this point, but you see the one, actually 228, 22 and 38. Ah, right. 38, 22, there we go. Those 2 paths from there. Okay, so anyway. And I actually automatically, for this data, I didn't have a target and a target and internet accessible node set up for it. So I'm choosing them essentially by using analysis of the graph. The target is basically, you can use an eigenvector centrality analysis to figure out for any graph what the most central node is and what the most peripheral nodes are. So what I did was I made the most peripheral nodes, or a random selection of the most peripheral nodes, the internet accessible nodes. And I made the most central node the target. There's a certain amount of randomness in this, but it works pretty well. Now, so we have the actual output, and we have this somewhat nicer, there we go. Sure, of course. Yes, it's saying, it's exactly that, because we set the distance metric for this graph to 2. Not in 2 hops. There are other ones, so if I originally set it to 3, so going back up here and just say, okay, we'll make that 3, and we get more paths, and then we go down, we just rebuild the graph, and you can see that now there's a 3 hop from 104 up here to 238 to 16 to the target. This is just path. I haven't imposed the vulnerability yet. I'm trying to. This is just getting the toes into the water here. Now we're actually good to bring it up. Let's add vulnerability data to this. So there's lots of sources for vulnerability data, and thank you. Thank you very much. That's very helpful. Wow, great timing. There's lots of sources of vulnerability data, but I'm cheap, so I'm not going to use any of them. I'm going to use a free source. Now, what we want to do is take that vulnerability data, extract the information we need to add arbitrary weights to the graph, and then see what changes. Now, because I said I was cheap, we're using the National Vulnerability Database. Sorry. The advantage is open source. It's community created. It's comprehensive. The disadvantage is that it's what it is. It's a complex data structure, and it's not really optimized to actually get the answer I was looking for. So, I mean, this is, so just basically, their files is, again, a bunch of files, 50 megabytes of stuff that looks like this. You see the point. It's not friendly. So I went to one of the basic tools I use for almost everything. I dumped it into Elasticsearch. Again, free, works well. You provide your own tech support, fine. And then so from that we can say we have for the Nmap data, we have the service on each port on each host. So then we can search for the vulnerability information associated with that service on each host. And so then we can use that to then reweight the graph based on the vulnerabilities. And we'll do that right now. So we have the vulnerabilities already. Let's apply it to the graph to get a new graph. And then we just get so for the distance of, so here we have real distances, target distance of less than or equal to 9, same target, same internet accessible host and same target. We have, what is that? 1, 2, 3, call it 4. And so we can then draw it. So we have this, make it a little smaller. Oh, we can see that. So you can see that, again, we have a very different, we have a different looking graph. So the same internet accessible host, but different paths to the target. And of course, we can also change the weight. So we could reduce it if we wanted more, say, reduce it to 7.0. So we get, that's ugly. Anyway, you get the idea. We can also increase it. So we could increase it to, say, 11. And I have, because there's, right, there's very few, we can't improve that very much. Anyway, so it gives us the vulnerabilities there. And basically for each host, at a certain point you have multiple vulnerabilities on each host. And I wanted to combine them in a relatively straightforward way that still gave me a single number. And so I used harmonic averaging, which essentially is a way of saying a lot of the people will tend to use the most vulnerable of the opportunities they have to get onto a particular server, but they might use a less vulnerable one. And so we weight those together using the harmonic mean. Also, in the vulnerability database, the scores are all the larger numbers being more vulnerable, but everything was set up to have shorter paths, to do shortest paths underlyingly. So I basically inverted the weights. So they were actually more convenient for my purposes. And so we actually, for each of the servers in the small set, we have a vulnerability weights that looks something like that. Now, okay, we're fine. But it's kind of boring to only look at 13 nodes. So let's see what we get when we create a large graph. And so let's spin it up. We wait for a few seconds, and so now we have 1,313 nodes and 17,470 edges between them. And the target is 10, 10, 22, 228. Now, we can get do it by distance. So we have, with a distance of 3, if we do a distance of 2, we get, three 2-hop links from the periphery to the target. And with 3, you can see it's a lot more. Now, this is a pretty big graph, and so what you do is if you try to actually draw that graph that I was drawing it before, you get a piece of beautiful modern art. So that's not really that useful, to me at least. So I thought, well, why don't I actually create a different way of drawing the graph that only actually includes the paths and leaves out all the other nodes. And so I don't get drowned in the big blue cloud. So we can do that. And so we get something, this is for the, I should have said, this is for the target of 3. We get something that looks a bit more friendly. It's not friendly, but you can actually kind of read it. If you want to go back and say, well, I was actually wanted to look at the really smallest numbers. We can then go back and then draw that. And we get something that's, you can't get much easier than that. And these are all the two hops from the shortest distance. This is then before the vulnerability information was added to the large graph. So we get something pretty straightforward. But we can also increase the noise, as we saw before, to get something that's more comprehensive. We have the vulnerabilities for the large graph, too. So we can just apply them. And now we're at distance 5 for this. We get the vulnerabilities at distance 5, and there are none. Let's increase it to 7. 7. What do we get now? Oh, there we go. So at distance 7, we get probably half a dozen. So we get a nice, that's what we get with at the distance 7, we get this vulnerability graph where we have the host here and the paths that lead to it from the periphery. Oh. Mm-hmm. We can look for, also we can increase the weight here so we can get a slightly, so go to 8. And then redraw the graph. And we get something, again, a little more comprehensive, a little noisier, more hops, but more of the same thing. Oh, sure. That's, well, we have, you've gotten me at a point where I don't know how, I'm using a graph drawing package. Now we can look at the actual paths here. So we have, so take the first one. Its weight is 6.04. We have a couple at that weight actually. 3, it looks, come on. 3 at that weight. And they're all look like 2 hops. And they are, of course.
To directly answer your question, it is a prioritization question. So you've got this nice long list. The first ones you should take action on are the ones that are immediate adjacencies to the target. Right. And then it's really just a question of diminishing priorities as you get further away from the target. And so you could imagine this, and this is early days on this approach, and again, we're releasing this out to the community. What John has done here in the Jupyter document, it fully elaborates everything that he said textually, so you can literally read this like a story, and then it explains the math. You can run the math right there just by clicking return, see the resulting charts, and continue the journey. And the point here is that we want to make it open to the community so that you could plug in Rapid7, you could plug in really whatever you want and get these answers with more consistent, reliable, familiar data to your internal operations. It's the same algorithms, it's just some light hooking of different APIs.
Thank you. So that's, again, as Peter said earlier, we have the code in the repo. The notebook will be going up, in case I had changed it during the talk, it will be going up after the talk, along with the data. If anyone, I assume most of you needs to know at least a little bit about Python. You need to install that. There are a couple other libraries, third-party libraries you would need to install as well. And also Elasticsearch, which is actually, given it's a large Java application, is actually fairly easy to install and use. And that's it. And now we'll go back to Peter. Thank you.
So certainly open to any questions. I think the too long didn't read on this is that right now we take slices of data by having fixed point perspective of our scanning of the network. And if instead we take slices of data from the perspective of every node in the environment, what you start to look at is this cube of data. And this is a familiar topic to both John and myself. My background is from Endeca Technologies, the company that invented faceted search, which of course today is just commonplace on every website you ever visit. And John was the chief data scientist of Ativio, which was the data lakes company, or is the data lakes company. And really what this is about OLAP modeling and faceted search, discoverable navigation, where you structure your data with multiple faceted views that if you can rotate and reorient your perspective on the data, you see different outcomes. And that's exactly what John has done here. He's taken individual slices of data from the vantage point of every device in your network and looked for the commonality across those data sets and joined them together so that it's now structured as this big interconnected mesh, a graph, and you only have to reorient your view of the graph to see different data sets, different results, and then you can augment the data set just by superimposing new data on top of the graph topology. So a super powerful, super flexible way of looking at network topology that gives you every possible multi-dimensional vantage point from every device, everywhere, always. So that's it. Any questions? Happy to answer. Yeah, go for it, of course. Hit the nail on the head. So that is not what Edgewise does, but for the purposes of this project, yeah, you hit the nail on the head. And for anybody who didn't hear him, really the point is that you're going to go through a remediation process as you learn data like this, and you prioritize these fixes. And really the point is that you're going to regenerate this data set by doing another Nmap scan across all of your systems at the rate that you remediate, right? Because you want to see those changes reflected in the graph. So you're continually doing these Nmap or it could be Rapid7 scans, aggregating the data together so that you can see how your landscape is changing over time from a vulnerability, exposure, and multi-step attack path perspective.
It seems like you chose prioritization based on eliminate the shortest path. I guess you could actually prioritize in a different way. I saw there was one of those graphs, there was a bottleneck. You remediate at one of those sites, it would block four paths all
Yep, choke points it's a fantastic point. So if you see a common node that is the intermediary for a subgraph, so it's a topic John didn't get into, but he educated me on it. So let's see how well I can relay this. You've got graphs that are highly interconnected, but off of those graphs are subgraphs. And where they interconnect is this join point that if you can block the vulnerabilities at that point, you fracture the graph. And it means that to the target, there are fewer possible paths that arrive at that ultimate target. But it doesn't change the fact that your highest priority is adjacencies to the target itself. So things that directly talk to or to the target. And then after that would be these choke points. And then after that would be things that directly touch the internet. Those are the ingress points, right? You clearly want to lock those down. Any questions around the table? Go for it. All right, with that, thank you so much.